My name is Tim Eichner. I would like to welcome you to an iGET concept module. iGET is a National Science Foundation project for remote sensing education. This module is intended to introduce you to the topic of band combinations, with a very brief introduction to the electromagnetic spectrum and how we perceive this energy. We're constantly bombarded by energy from the sun in the form of electromagnetic waves. This energy is categorized for our convenience into 7 different categories ranging from radio waves to gamma waves. We view a very narrow portion of this electromagnetic spectrum we refer to as the visible portion of the spectrum. This energy within the visible spectrum needs to be differentiated so that way we can see images rather than just white brightness. Our eyes accomplish this task by differentiating 3 different bands of energy: the red band, the green band, and the blue band. Within our eyes, sensors actually react to energy within these narrow ranges and shuttle that signal to our brains, where our images are formed. Let's take a look at how this is accomplished by investigating the energy of this circle. If we separate the circle into the 3 primary bands of red, blue, and green, we can see that there's an amount of reflectance, amount of energy that's actually being reflected to our eyes. Now, if all 3 are reflecting 100% in each of the blue, red, and green bands, what color do you think we would see? Well, if we actually assign the color values to each one of these light energies or intensities, we would be able to see that our brain interprets this energy as white. Now, if we adjust the energy just slightly, you can see that the color our brain actually sees is much different. In this case, we're seeing a bright green because the green portion of the 3 bands is most greatly reflected, whereas the blue is the least reflected. I would like to demonstrate how this works within digital photography using a picture of my kids. This is Conrad and Sally. Now, as you know, a digital image is made up of small pixels. And what we see here on Grandma's Cozy Cabin is a bunch of yellow windows on a red background. But that's not actually what the camera sees. Let's look at what the actual camera senses. As you can see, the camera actually detects the intensity of reflectance within 3 different bands: band 3, 2, and 1, or otherwise known as the red, green, and blue bands. Now, the intensity of reflectance is recorded by the camera on a digital number scale of 0 to 255. So the brighter the number, the higher the digital number, and the brighter the cell or pixel is. The less reflectance that occurs, the lower the digital number and the darker the cell. And Landsat actually uses this same system. And Landsat missions 1 through 7 record this reflectance on a scale of 0 to 255, whereas Landsat 8, the most recent Landsat mission, records it on a scale of 0 to 4095. We can investigate this in a little bit more detail just to see the actual cell arrangement and their respective values for just band 1. And top left cell or pixel is 140 digital number, and the highest digital number in this arrangement is 247. So the one cell that's nearest white. Now you may be asking, how does a camera or the information from a camera turn into an image that actually makes sense to us, a color image? Well, just like our eyes sense reflectance and our brains transform it into an image that makes sense to us, a camera senses reflectance and a computer actually transforms that into an image that makes sense to us. And it does it by assigning colors to the reflectance within each one of the bands. So red is given to red, and green to green, and blue to blue. And once that color is assigned to the reflectance value, those 3 colors are then blended together to form the image that we actually see. Point-and-shoot cameras that we use only capture 3 bands within visible spectrum. However, Landsat satellites actually capture bands beyond the visible spectrum. Three additional bands that we're going to focus on include band 4, 5, and 7, or the near infrared, band 4, and the two shortwave infrareds, bands 5 and 7. The surface of the Earth reflects light energy in each one of these bands differently, as reflected in this array of images from Glacier National Park. Let's investigate one phenomenon that we're all comfortable with or familiar with, and that is snow. As you know, snow is white because it greatly reflects light within the visible portion of the spectrum. However, is snow always white? Particularly if we're talking about the near infrared and shortwave infrared portions of the spectrum. How does snow reflect this energy? Let's investigate this. Let's take a closer look at a glacier in the park. This is Sperry Glacier, and as you might predict, the visible bands, bands 1, 2, and 3, reflect light very strongly, and you can see the digital numbers range from 170 to 132, fairly reflective. However, if we transition into the infrared portion, the portion that we can't see, band 4, the near infrared band, its reflectance starts to diminish. And if we look at bands 5 and 7, the shortwave infrared bands, you can see that the reflectance is pretty much non-existent. So the answer to the question, is snow always white? Well, if we're just looking at the visible portion of the spectrum, the answer is yes. But if we're looking beyond the visible, the answer is no. Snow doesn't reflect light energy the same. And you can see it's fairly well diminished in the infrared portion of the spectrum. We use this knowledge of how land surfaces actually reflect this energy in order to build images. So for example, if we wanted to really highlight the snow within Glacier National Park, how might we assign colors to different bands and build what we refer to as a composite image to create an image for interpretive purposes? For example, what kind of image would we get if we assigned our primary colors to band 7, 5, and 1? You can see we end up with an image that really highlights the snow within Glacier National Park. So for interpretive purposes, if we look at this image right away, we see where the snow exists. Let's take a quick look at the different bands that we use and how it interacts with the Earth's surface. Band 3, or the red band, is a band that's very highly absorbed by vegetation because it's used for photosynthesis. It's also absorbed quite well by water. Therefore, water bodies within this band appear fairly dark. Band 2 is slightly better reflected by water than red, and it can actually be used to differentiate between clear water and turbid water. And in addition, it's very strongly reflected by vegetation. Band 1, or the blue band, is actually able to penetrate water fairly well, and is sometimes used for bathymetric mapping purposes. It can also distinguish between a lot of different land characteristics, including differentiating soil from vegetation and deciduous trees from coniferous trees. If we blend these three bands together to form a composite, what we end up with is a true color image. A true color composite approximates the range of human vision, and hence these images appear to be close to what we would expect to see in a normal photograph. True color images tend to be low in contrast and somewhat hazy in appearance. This is because blue light is more susceptible than other bandwidths to scatter by the atmosphere. Broad-based analysis of underwater features and land cover are representative applications for true color composites. A band we're going to use in another combination is the near-infrared band, or band 4. This band is strongly reflected by healthy vegetation. If we combine this or assign this to the red band, and band 3 to the green band, and band 2 to the blue band, what we end up with is something we refer to as the near-infrared composite. This band combination, which has dropped out the visible blue band, creates a near-infrared composite. Vegetation in the near-infrared band is highly reflective due to chlorophyll, and a near-infrared band vividly shows vegetation in various shades of red. Water appears dark, almost black, due to the absorption of the energy in the visible red and near-infrared bands. We're going to investigate one more band combination, and one that actually includes a shortwave infrared band, in this case band 7. Band 7 is very strongly reflected by soil and bedrock, and as we saw earlier, is also absorbed really well by snow and ice. If we assign band 7 to the color red and band 4 to green and band 2 to blue, we end up with a false color composite image. A shortwave infrared composite image is one that contains at least one shortwave infrared band, either 5 or 7. Reflectance in this region is due primarily to moisture content. These bands are especially suited for camouflage detection, change detection, disturbed soils, soil type, and vegetation stress. When it comes to band combinations, ultimately the choice is yours. It depends on what message you're actually trying to get across. Are you trying to present the natural landscape or provide an indication on vegetation health? Perhaps you're interested in just identifying specific features on the landscape, such as glaciers, or maybe urban areas or disturbed sites. Each band combination tells a very unique story. You have to choose what story is yours.